Good morning, everybody. It's a pleasure to have you back here this morning for our last morning session. And we are going to start with, I was saying, Davide Carazzato, but he's going to speak about the joint work with Walter Fratelli. The title is Symmetry and Boundedness of Minimizer of some Non-Local Energy. Please.
Many thanks for the introduction, and thank you, Alessandra and Mattia, for inviting me. So today I will talk about this topic, and the first thing to be specified is which non-local energies, because it is a bit vague. And what I studied are energy that are of interaction type. We can call them in this way, where you have a kernel G that measures the interaction between particles at a certain distance, let's say. And we define 4 measures defined on Rn, okay? Of course, you have already seen energies of this type, for example, when you've seen Coulomb energies, for example. But you should not really think about the Coulomb energy for this talk, because it is not okay for the minimizers. When one thinks to the minimizers, it is not very interesting. In fact, there are no minimizers if you put as G the kernel that is the Coulomb kernel. So I will start with a very brief introduction of this topic and of the literature. Then I will pass to the symmetry issues that arise when one studies this problem, and this will be, let's say, a review of many results that are present in the literature with minor contributions, and then I will pass to the boundedness of the minimizers that also in some cases. So we would like to say that when we study minimizers for this kind of energy, they are L infinity. They are measures with density with respect to the Lebesgue measure, and this density is bounded. Okay, this is the final goal. So when if you ever open one of the articles that I've studied, you may look some pictures that are of this type when one looks at the kernels. For example, something like this, or something like this. Okay, and if you want a formula that is something that is useful when you do computations, of course, people use something like this. Or something when alpha and beta are positive, or something like this. Again, with alpha and beta positive, with some relation between them. You may wonder why. Why do you choose these kernels and these particular shapes? And the reason is that if you, as I anticipated, if you choose just like the Coulomb energy, you forget about the positive power, you have no minimizers very easily, because if you fix any measure, you like take the push forward through a dilation, you're decreasing the energy. Okay, very easy. The same problem, not the same, but an analogous problem happens if you forget about the Coulomb energy, or something like that is decreasing close to the energy, close to the origin, because the minimizers are just deltas. Okay, so in a sense, these kind of kernels are the easiest possible where you find something interesting. And notice that if particles could forget about their auto interaction, they would just put themselves at the right distance where you find the minimum of the kernel. That's of course not possible, because you have the energy in zero. But this should produce some shape that are not not really easy to understand. They might form patterns, or something sometimes very regular. It really depends on the kernel. Okay. So you see that these kernels both diverge at infinity, and this is useful for the existence questions because it is very easy. In fact, this is not something that I will touch, but it is really not hard to see that if you have G that is non-negative, lower semi-continuous on the whole Rn, and G of X is diverges at infinity, then you find existence, and you not just find existence, but you also find a given radius where that is a bound on the diameter or on the radius of the support of your minimizers. So you have no mass that escapes at infinity, and if you look at your function, most of the times we'll have a singularity just in the origin. So if you look at the derivatives of G, they are all bounded away from the origin in our mind. And these kind of energies have enjoyed a great interest in the mathematical society in the recent years, because they are used to model some physical phenomenon that are some particles, some individuals, some chemicals that interact in this way. They would like to not to get too far apart for some reasons, and not stick together too much. For some reasons. This is not that. This is not something that I've studied, but many people justify the interest in these kind of energies because there is this interest in the applications. And for example, the parabolic point of view is something that has been studied. Namely, you can try to do a gradient flow with respect to this energy. But I didn't study this evolutionary point of view. I studied the ground states of this energy, and also this has been already studied widely with some specific choices. In fact, most of the time it is sum of powers that compete, or logarithms, or something very specific. So our aim was to understand if the results that one obtains are really depend really on the choice of the functions that are very specific. If you want to model something, you may want to not to choose 2 powers, for example, or if there are some general features of G that guarantee to find something interesting. Okay. Just a last comment on the literature. One, of course, might put any constraint that he prefers on this function. In fact, the first instance of this kind of energies that I found was the first in my experience, I mean, not in the literature, was in a paper by Frank and Lieb that I think it was published in 2021. And where, they used this kind of energy with the sum of a positive and a negative power, and they put a constraint that was an infinite constraint. Okay, this of course trivializes our question, so the boundedness. In fact, they were interested in something different. That was the shape of the minimizers when one constrains the L1 norm with a number that goes at infinity, and it turns out to be a minimizer in this case. When you take your L1 constraint large enough, and this, of course, we that's clear that putting constraints changes a lot the problem. This happens as well in this case, because if you look at our energy, if you don't put any constraint on the L1 norm, you see that it is too homogeneous. When you scale mu on the height, you simply find like if you scale by lambda, you find lambda square times the energy. So then our problem is very different, and we can constrain the mass to be 1. Okay, so that's just one thing that we don't have to care. So we will minimize among measures that are in the probability measures. Okay. And now we can look a bit to this problem, and we can find the invariances in tests. It is immediate to see that this translation invariant. Okay. And it is also rotationally invariant if G is symmetric. Okay. And this already, let's say that if you want to prove symmetry, this might be interesting, because you see, maybe you can hope, and it is true in sometimes, that your energy is convex in some sense, like up to translations. And if it is convex, then it is, and if your G is symmetric, then it is easy to find symmetric minimizers, simply because, so let's talk about, symmetry. And from now on, my function G will be symmetric to simplify things. So G of X is just a function of the modulus of X. Yeah, the notation is very sloppy, but I hope you will forgive me. And okay, if you know, if E is convex up to translations, let's say, then you find minimizers. There exists a minimizer of E in the class of the radial measures. And it is very easy, in fact, because you can find minimizers with very mild hypothesis. And you can try to rotate it and take a convex, like fixing the barycenter, for example. You rotate around the barycenter. You take the convex like the average between these two measures. Okay, so let's say that you have mu rotated. Okay, and you pick mu bar that is 1/2 mu plus mu r, and it is again a minimizer. Okay, because mu rotated has the same energy as mu, because your G was symmetric. So you found something that is more symmetric. You can average with smaller and smaller angles, and if you want, you take the limit, the weak limit, and you end up with a minimizer that is symmetric. So why is it? So in a sense, the problem is trivial. So the symmetry issue is trivial when your energy is convex, but it is the only case where people can find some symmetric minimizer. Okay, so what we would like to understand is when our energy is convex. And it turns out to be, well, it can be characterized in this way. Well, now let me give a definition. Okay, I have, that is a definition about a kernel. I call H just to not to confuse it with the original one. You have a function H that is, okay, let's say locally integrable just to find some energies, some measures with finite energy. And we take it, okay, lower semi-continuous if you want. Then we call it strongly positive definite. If the following holds, okay, maybe I'm finishing the space. I hope you can read from, yes, I hope so. If this thing happens, okay, when I will do this thing, hopefully it will be not too confusing. For any mu and nu, let's say with compact support in Rn, with the same barycenter that we can fix to be 0. Okay, I didn't say what is EH, but EH is simply the energy computed with the interaction kernel that is H. And you can define also between two different measures. Okay, so that's the definition. And in fact, having a kernel that is strongly positive definite is equivalent to asking that your energy is convex. You simply, because this energy is quadratic in mu, so you simply expand the things when you try to do this. You do. Okay, and this is okay. It should be something like this times this thing. Okay, so that's okay. That's equivalent to say that your energy is convex, or at least if you have a given kernel, and asking that it is strongly positive definite. So the question is now to characterize these kernels, and this is not easy. This is we have just partial results. For example, it is possible to prove this theorem that now I state in a very sloppy way. If you have H that has that is subharmonic outside of the origin, I always assume regularity that is outside of the origin because yeah, sure. Yeah. I'm sorry. Yeah, that's equivalent. Well, if you want, it is to work with measures that are non-negative, so that you can. Okay, so you can use lower semi-continuity and stuff. Okay. So some conditions to find some convex energies are to ask that the kernel is, for example, subharmonic out of the origin, and that the limit of h of x, as x is going to plus infinity, is the infimum of h. Infimum of h. In this case, you can prove that it is strongly positive definite. Or another possibility is to ask that the Fourier transform is non-negative as as a Borel measure. And again, you have that the lim sup of x at infinity is finite. And in this case, and this is intended in the distributional sense. And in this case, you can say that it is just positive definite. And what do I mean? I mean that this condition holds not for measures, but for densities, like bounded densities. Okay. And this, okay, at the beginning, we thought that they were like equivalent, to be strongly positive definite and positive definite functions were the same class. But we are not really able to prove that. We are able, of course, there is an inclusion, but there is an issue here, because we are not always able to prove that we can approximate in energy a measure with L-infinity functions. Okay, if we were able to do that, then we would be able to pass from one to the other. And that's a bit unpleasant for now, but probably we are not good enough ourselves. Just okay, a comment about this. It is not trivial. Even other researchers, in fact, needed some approximation in energy theorems. And an example, well, what we could do is to say that okay, if you have H that has let's say some reasonable hypothesis, but you ask that this condition also for some alpha in 0n, then you can approximate in energy, more or less. You should add something else, but this is the most specific hypothesis, not so, yeah, sure. Sorry, yeah, sure. In fact, the positive definite functions were already defined in the literature, and there are those functions H where these condition also with densities, with bounded densities, L-infinity densities. Okay. And okay, in fact, the positive definite functions that are also continuous were characterized. I don't remember the name of the theorem. Precisely with this condition. Okay, so it should be natural that this is what we should ask, but that's not clear if it is so easy to pass from positive definite to strongly positive definite. Yeah. No, it's H. This is the Fourier transform. Sorry, I'm sorry, I didn't tell this, but if okay, you have a kernel H, and you can ask either that the Laplacian is positive outside of the origin, or that you compute the Fourier transform if you're able to, and you see that is a non-negative Borel measure intended in the tempered distribution sense. Okay. I don't know. I don't know. For sure, the second one does not imply the first. That's easy. For example, a Gaussian. But the other one, I don't know. Probably some people more expert than me in harmonic analysis could help. Okay. But okay, if you have a function that you see is not too singular in 0, then you can approximate in energy. Then for any mu with compact support, let's say, that is of course sufficient for our scopes, there exists a sequence μj that are okay in L infinity, but they are smooth actually, such that μj converge with start mu, and the energy of μj is going to the energy of mu. A little comment on this fact. Well, how do you do that? Of course, by convolution. That's the idea. And this condition is needed to say that well, when you consider that energy mu computed, that energy E computed not on mu but on mu convoluted with something, it's the same as computing the energy E with a different kernel that is G doubly convoluted with the function that you are using. Okay, and what you need is that this new kernel is like comparable in height with the original one, with H. Okay. So far so good. This is just to all of these results are there just to tell you that we have examples of positive definite kernels. In fact, for example, there are these, okay, let's say, if you take h of x equal to any negative power that is between 0 and n, this is strongly positive definite because you compute the Fourier transform and it is another negative power. Okay. Or h of x equal to the Gaussian, for example, or h of x equal to the logarithm in dimension 2. Okay, these are all positive definite functions. But now you may notice that, and also this theorem is telling you that we are able to find some positive definite functions that are bounded at infinity. That's bad because I told you that we can find existence when we have a function that diverges, and in fact we are able to find very few functions that are positive definite and that diverge at infinity, but they are very specific. In fact, you can see that h of x, that is x squared, is positive definite, and with this is really easy. With some work instead, you can do this. You can say that x to the alpha with alpha in 2, 4 is positive definite. It's strong. Okay, is positive definite, and this is due to Lopez. I think that published in 2019. Not sure, but okay. And so we have very few examples of these functions that are strongly positive, that are positive definite, and that diverge at infinity, and that's a bit of a problem. I mean, it is a bit restrictive, but for now, that's what we have. Okay, this I think that this concludes what I wanted to say about symmetry. I think okay, I should be on time, and now I'll pass to the boundedness results, and you'll see that the symmetry are not there just because they are interesting on their own, but they are kind of necessary for the boundedness that we are able to prove. I'm sorry, I'm erasing these just because you have this condition here. It is what we need. And okay, so I can pass to the boundedness of the minimizers. And now I'll write the our statement more or less, and then I will comment on that. So you'll see that is Yes, please. Sure. Sure. You get that you have minimized, if you have, sorry, thank you for pointing that out. If you have a function g, that is, for example, x squared plus 1 over x to the alpha with alpha in 0n, then you find minimizers. If you try to minimize this energy with this function g, you find minimizers that are symmetric. See? Yes, and that's equivalent to say that your energy was convex up to translations. No, this was known. Let's say that this approximation in energy we didn't find anywhere. Okay, so this condition is also useful for the boundedness result, and something that was almost there was that if you have a subharmonic function, then it is strongly positive definite. Yes, and actually, in this case, in this specific case, it is the unique minimizer because up to translations, of course, because this negative power is not just strongly positive definite, but it is strictly strongly positive definite. That means that that inequality is strict when you have different mu. Okay, so you are very happy because you have symmetric measures that are much easier to handle. But we will see that not really all of these powers are okay for us, for now at least. And in fact, other questions up to now? No? Okay. Okay, now I write a bunch of hypotheses on G and the theorem. Okay. So okay, we have G that is radial. That is okay, L1 lock. C2 outside of the origin, and for okay, let's say subharmonic outside of the origin, and that's okay, let's say this. We ask G to be decreasing, and sorry, I write in another place. G is decreasing and G prime, okay, since it is negative, it is increasing in a small neighborhood of the origin. That is something like this, like a negative power. Okay. And okay, this is sufficient. Plus, okay, if you want, G of x is going to plus infinity as the modulus of x is going to plus infinity. Okay. This is the starting point. Then what can you say? You can say that you have an L infinity bound for any minimizer of E with some additional hypotheses that are, if you have that the support of mu is convex, and this property also okay. So you see that the first point is you have what you want, provided that you can provided that you start from a minimizer that has convex support. That's a lot. We in general don't know how the support is made. And if you have a function g that is singular enough in the origin, that is what should provide an infinity bound. And if you have a function g that does not explode, that's not so reasonable to expect an infinity bound. Okay. So we have this condition that is, let's say, a priori on g and something on mu. And this is one case. The second one is that you have, okay, an infinity bound, again, for any minimizer in the radial class. Okay, if, again, we have this property star that is g is singular enough. And finally, we can find an infinity bound for some minimizer. Again, in PRAD. And okay, for these, we should also ask that G is strictly subharmonic in BR. Okay. So in these 3 points, you see different hypotheses and different conclusions. And in a sense, it is sufficient to prove the first one. The second and the third follow, well, we don't need to really do an infinity estimate. They follow from the first one, doing some work. So I would like to talk about the first point, that is where it is more important that our function g is subharmonic. And then I will talk about the second and third point if I have time. Sorry, is there any question? No. Okay. So the strategy here is in a sense very simple. You okay, for the first time now, I'll use the first variation of the energy that I've never written so far. So finally we use it. And the strategy is to prove, well, to take any minimizer mu, take a convolution with the smooth kernel, and prove, you would like to prove an infinity estimate for these modified measures that is uniform. If you can do that, you are okay. And how you do that? Well, in the first point, you see that you have a convex support, so a well-behaved set. So you can look at your modified measure. You can look at you can take the maximum point. If it is close to the boundary, then you work out some estimate, and you can do that thanks to really thanks to the fact that G explodes more or less in 0. If instead you are inside of the support, you'll need to use that you have a minimizer, so you have a constant potential. That is something that I'm going to define in a moment. Okay, so now let me define the potential generated by a measure mu that I call psi. That is a function that is pointwise defined. Okay, and this function is useful for our problem because you can take variations of this energy, and you can see with okay, with measures that are smaller than mu, but that okay, it is easy to see that you have this thing moreover, you have so your potential is constant, mu almost everywhere. So in the support, you have that it is smaller than the same constant in the support of mu, and the potential is larger than the same constant outside of the support. Okay, and this simply follows taking variations with measures that are, as I said, smaller than mu. In like the first, the total variation is smaller than mu. Okay. So how do we use this condition? Well, we use this to prove this estimate that also in the first case. So if you have mu that is a minimizer of E with convex support, then what you have is that the measure of any ball of radius rho centered at a point that is on the boundary of the support is controlled in this way for any x in the boundary of the support of mu, and for any rho small enough. And the constant here really, well, it depends on G and just on G. And indeed, C depends only on the function G that is restricted to like R, that was the radius where you have that G is decreasing, that is something, and the bound on the diameter that you have on the minimizers. Okay, you have just so you look at your function G, but you don't really care of the function G close to the origin for that constant. And to see, well, this lemma indeed, okay, one can write details, but it is easy to see that something like this holds, because you take your convex set, you pick a point on the boundary, you pick a ball of radius rho, okay, so this is rho, and you compute the potential in the point x and in a point that is outside of the convex set. So you would like to compute this plus, let's say, 2 rho times a vector v that is orthogonal to the convex set. Okay, and you know that this is non-negative, but you look at what is happening here. So this is the integral of g of x plus 2 rho v minus y minus g of x minus y in the mu y. And what is happening? You are getting far away from any point in the support, and this is where you use that the support is convex, precisely here. So any point is getting, if you compute the potential here, you look at any point on the support and you are looking at them from far away. And our G is something like that, like, namely it is decreasing close to the origin and then it is regular. So what you are seeing is something that might increase, but at most in a Lipschitz way, right? So you have that. Okay. No, I cannot do the trick as before. So So what you do, what you see is that psi mu on x plus 2 rho v minus y minus psi mu of x is smaller than, well, a constant that depends just on the positive part of the derivative of g times rho, if you move of rho, plus something that is, well, if you look at the contributions of these points, okay, you see that you are getting away of something that is like a constant times rho. But their g is decreasing, and it is decreasing very fast. So you get a constant times g prime of rho times rho again, something like this, okay? And this is non-negative because of the optimality conditions. So you simply, and times, sorry, so you get times mu of b rho. And this, since g prime of rho is negative, provides a very easy estimate on the measure of a ball close to the boundary. And this also tells you why this lemma is really tailored to this, or better, this hypothesis is really tailored to this lemma, because you have an estimate on the growth of g prime. And this, if you take convolutions, that condition is precisely what is telling you that you have small mass close to the boundary, small L infinity norm close to the boundary. Okay, that's an easy computation. So what is left to do is the estimate inside, where we really use the potential is constant. And of course, I didn't say this, but if you take mu convoluted with some convolution kernel theta epsilon, your potential will be constant in well inside of the support. Okay, so that's what we use. Okay. And now we would like to reduce to the simplest possible situation. And we still keeping the fact that our potential is constant inside of the support. So what we do? We take our new measure mu epsilon, that is mu convoluted with theta epsilon. We say, okay, the maximum point, if the maximum point is close to the boundary, then we are okay with this estimate, that estimate. If it is inside, we want to do something. And what we do is to symmetrize this measure around that point. So you pick x bar in the support of mu. That is a maximum for mu epsilon. Okay, and you rotate. You take you take your mu epsilon. You rotate around x bar, and you take the average of these rotations. So you end up with a measure, with a new measure that has constant potential in a neighborhood of this x bar, and it has well, we end up with a mu tilde, that is the radial average around x bar. You see that the maximum point of mu tilde is again in x bar. That was the maximum for mu epsilon. It has again constant potential in a neighborhood of x bar. And now you would like to prove an infinity estimate for mu tilde. Then you are done. Okay. So we can do that. We can do that. And now we use finally that our G was subharmonic. Up to now, we didn't use for that lemma. So what do? We have our mu tilde that is radial, that is perfectly smooth, for example, at least C2. So we look at this psi mu tilde computed in a point x minus psi mu tilde computed in x bar. Okay. We know that it is constant, this potential, but and we would like to imply that mu tilde in x bar is small, is not too high. And okay, this is the integral of g of x minus y minus g of x bar minus y d mu tilde. Okay. And we divide this integral in two pieces that are like an integral in around br of x bar minus the integral on the complement. Okay, plus, sorry. This piece here, so in the mu tilde, as a function of x, is C2 in a neighborhood of x bar. Okay, that's perfectly regular. So in fact, its second derivative is bounded. Okay. And this is actually sufficient for our interests, because we will see that instead the other part has a second derivative that is bounded by something that depends on f of 0, and is bounded like it is. It will be negative definite, the action in x bar of the remaining part. So this will be sufficient to say that your f of 0 will be your mu tilde of 0 is bounded. So now we do care about this. So let me write down this thing. So okay, let's say that I call psi 1 of x equal to the integral of br of x bar g of x minus y d mu tilde y. So we compute psi 1 of x minus psi 1 of x bar. What is this? Well, that's well, that's g of x minus y minus g of x bar minus y. Okay. Times d mu tilde y. So what do I write it here? So mu tilde is actually a function. So you have mu tilde of y, and now I do this plus sorry for the handwriting, plus the same integral times mu tilde 0. And okay, the first now we look at the first part, and we see that in well, in a small neighborhood, of x bar, we have that this piece here is bounded by sorry, this was x bar. We can say that this piece here is bounded by a constant times the difference between y and x bar squared. Okay. So you can see that all of these actually making, okay, let's cut a little bit these computations, but we have you can see that this is smaller than like if you integrate, let me write in this way, of all of these times f times mu tilde of y minus mu tilde of x bar, and this plus the integral of br minus b mod x minus x bar of the same thing. Okay, this is bounded very well. This is less than a constant times x minus x bar squared. And this is like a constant that does not depend on anything, like only on G. And this piece here, instead, is actually is negative, thanks to the fact that G is subharmonic, because you are integrating your G on some shells. So you're looking, if you look at a sphere around x bar, this piece is constant because you have mu tilde that is symmetric. You have that this piece here is subharmonic in there, so it has a minimum in 0. So it has the right sign, and we are very happy of this because we are left just with the constant term, the 0 order term. So this, we are lacking of this mu tilde in x bar times the integral of g of x minus y minus g of x bar minus y in dy over br. And this is a geometric computation. It is bounded, again, it is smaller than a constant that is not so relevant. So here I'll write an inequality times g prime of r times, okay, a constant. So you see that if times, again, x minus x bar squared. So you see that if mu tilde at x is too high, you have that your psi mu cannot have 0 second derivative in x bar. So it surely cannot be constant. And this simply tells you that your measure was not too singular, and indeed it was all'infinity. And okay, this is a point that we cannot we cannot remove this hypothesis of being subharmonic. That's something that in my my feeling is that it shouldn't be so necessary, because if you have if you have a kernel that is that has some growth in 0, if you have something that is more singular than that, you should find something, another minimizer that is again all'infinity. But up to now we cannot remove this kind of differential hypothesis on G, and that's I don't know if it can be done. But let me say that other results have been found with more specific choices of G, that is like the Coulomb kernel plus something that is bounded in some way. And so also in those cases, they can find some results. And well, saying that you have Coulomb plus something, or something that is more singular than Coulomb, like another power that grow faster in 0, is like again asking something on the Laplacian, okay, of G. So that's it is unclear if this is just an easy way to get the result, so that other people chose these conditions on the kernel to obtain L-infinity estimates or something more also, or if it is really needed. That's not clear. So I don't know, do you have some time or not? No. Okay. Perfect. So just a quick comment. The fact that G subharmonic is not needed just here, but also to pass from 1 to 2. And just a really quick comment. Why is this necessary now, but hopefully also this can be relaxed? Because when you look, well, how do you pass from 1 to 2? Is well, you pick your minimizer that is symmetric, and you look at the potential outside of the support. So you have, and you suppose that you don't have a convex support. So if you have a convex support, you have a ball, and you can apply the first part. If it is not, you have something here and something here, but an annulus with no mass. But then what do you do is, well, look at the potential here. It is subharmonic. So it is like increasing here or decreasing here. That's a very easy ODE comparison. And then you get a contradiction because you can prove that, okay, your potential was strictly larger than E of mu outside of the support. And you can prove that it should be continuous, actually, in this case, in this symmetric case. In general, we don't know. And also here we need, up to now, to know that the potential is subharmonic there, because of this ODE comparison. Otherwise, we don't know how to do that. Okay, thank you for the attention, and sorry for the overtime.
Thank you. Other question?
Sure.
The last assumption you wrote up here, up there, about the behavior at infinity of G,
yeah,
is just due to ensure the existence of minimizers.
Well, there are milder assumptions, but we use it to have. Actually, I don't know if under that milder assumption you have a uniform control on the diameter of the support. If you have it, then you are fine, because then your G is regular and you can do your estimates. Because sometimes it appears like the supremum of G prime in like R, capital R, where capital R is the diameter of the support of a minimizer. If you have this bound on the support, you're fine. Otherwise, I don't know.
Okay, so you also use it in the proof. It's not just in order to have some minimizer.
No, sure. We use to have minimizers with bounded support.
Okay, but just for this, say if for some other reasons you had minimizers with bounded support,
yes,
it would be enough.
Sure.
Okay, and that condition is not also necessary, right, to have minimizers with
this I'm not sure about. We didn't do that. We always supposed to have something that diverges at infinity for simplicity. I think that there is some bound, but up to right now, I'm not completely sure.
Okay. So anyway, it's used just in order to ensure a priori the existence.
Yes.
Okay.
Otherwise, you don't care.
Okay. Thank you.
I also have another question.
Sure.
If a kernel is not L1, what?
Well, L1 lock. That's something that you don't want to do, because in that case, even a ball doesn't have a finite energy.
Okay.
Because you slice, you integrate infinity all the times. So I think that you can prove that any energy has infinite. Any measure has infinite energy, I guess, because it is more singular than. Okay. Yeah, I mean, it is more singular than a density, so I guess that it has infinite energy.
Are there other questions? Okay, if not, we thank again Davide.
Thanks.
And we have our coffee break hour now.
Okay, we're going to close this workshop with the last speaker of these 2 days. So welcome Mario Schulz from Münster, who's discussing free boundary minimal surfaces in the unit ball.
Yeah, thank you very much for the introduction and the invitation and the opportunity to present my work on free boundary minimal surfaces. So all I'm going to present is joint work with Alessandro Carlotto and Chada France, respectively David Weigel. So Alessandro and Chada both have very strong roots here in Pisa, as you might know. But right now, Alessandro is moving to Trento and Chada's at MIT right now. And David is also going to be in Trento soon, as far as I know. So I'm trying to give a very introductory talk on the topic. I will give you a brief introduction about free boundary minimal surfaces. And I will show you many examples. Yeah? I mean, by now there are some known examples of these surfaces, and I will show them to you how they look like. And then I will present our main existence result. And I will also discuss the uniqueness question in the fourth part of the talk. And then we will have some time for discussion and looking at open problems. So let me introduce the setting and the notation. So we will only look at the three-dimensional Euclidean unit ball in this talk. Yeah? This is a very concrete situation, and it seems to be very simple, but it's already very interesting situation with many unknown questions. Yeah? So B3 is the closed three-dimensional Euclidean unit ball. And sigma will denote a compact surface, which in general has some genus G and some number of boundary components, which I denote by B. And most of the time we will assume that such a surface sigma is properly embedded in the Euclidean unit ball. So properly embedded in this case simply means that the boundary of sigma sits on the unit sphere, right? So and sigma is only touching the unit sphere along its own boundary, right? So sigma intersected with the boundary of the ball is exactly the boundary of sigma itself. Yeah? That's what properly embedded means here. So we do not allow interior points of sigma to touch the boundary of the ball. Okay. And such a surface is called free boundary minimal surface if the following equivalent conditions hold. First one being that sigma is a critical point for the area functional among all such surfaces in the unit ball, right? Among all surfaces with boundary constraint to the sphere, we look for critical points of the area functional, and such critical points will be called free boundary minimal surfaces, right? So now what you can do is to write down the area functional, write down the first variation of the area, and in this specific case with free boundary, and you see what kind of Euler-Lagrange equation you get. And as usual, you will see that such critical points must have vanishing mean curvature. But here with this free boundary condition, you would also see from the boundary integral that the boundary of the surface has to meet the sphere orthogonally, right? Otherwise, the first variation is not going to vanish. So equivalently, a free boundary minimal surface has vanishing mean curvature and meets the sphere orthogonally. So let's quickly recall from Anna's talk what the mean curvature was, right? So remember, you can, on any smooth surface, you can compute the principal curvatures, right? There will be a direction in which the curvature is sort of largest and an orthogonal direction in which the curvature is least with opposite sign, right? And so these are the principal curvatures, and if both of them add to 0, then the mean curvature is vanishing at that point and requiring it to vanish at every point in this condition. So let's have a look at the third condition. This is very specific to the Euclidean unit ball. You can require the coordinate functions on the surface to solve this Steklov eigenvalue problem. So if a surface in the unit ball, if the coordinate, if the Euclidean coordinates restricted to the surface are harmonic functions, and if the normal derivative along the boundary is given by an eigenvalue sigma times the function, where sigma is equal to 1, then the surface corresponding to these coordinates is going to be a free boundary minimal surface, right? So this is one of the reasons why the unit ball is so special and so interesting, because while 1 and 2 make sense in any ambient, the third one is only true for the Euclidean unit ball situation. Yeah? So that's why the particular interest in this case comes from, as you see in the next slide also, right? So let me tell you a little bit more about the Steklov eigenvalue problem, right? I mean, that's the reason where this renewed interest in these surfaces comes from. You have a question right now? No, I mean, you can formulate this problem in higher dimensions as well, and you get a similar definition. Yeah, this works in high dimension also. Yeah. Yes. So one of the reasons why we restrict to the 3-dimensional case is that we have a very easy classification of topology, right? For surfaces, it's enough to give the genus and the number of boundary components, and that's it. Yeah. In higher, you can, of course, ask for free boundary minimal hypersurfaces in higher dimensions, but this is already too complicated. So this situation has already exactly the right complexity, as we will see during the talk. Yeah. So what is this Steklov eigenvalue I was speaking about? So here we have again this Steklov problem. So we ask for harmonicity in the interior, and we put the eigenvalue somehow as a boundary condition. Yeah. But even in this case, you can define the first eigenvalue variationally, as you would do for classical Laplace eigenvalues, right? And you can define this first lowest eigenvalue variationally, as you can see here on the slide. And then there's a very famous theorem by Fraser and Shane, which states that so if you look at this first eigenvalue as a function depending on the surface and the Riemannian metric on the surface, right? You can ask for which situations is this largest value, right? Now you notice, okay, it's depending on the scale, right? So let's make it scale invariant. One way to make it scale invariant is by multiplying with the length of the boundary with respect to the metric. That's the quantity we see here. So now the theorem states that given a surface sigma, let's find a metric, a smooth metric on that surface which maximizes this scale invariant first Steklov eigenvalue. How does the surface look like? So if you find a smooth metric maximizing this scale invariant first Steklov eigenvalue, then there exists independent first eigenfunctions corresponding to this Steklov eigenvalue, which sort of as coordinates give a branched minimal immersion into the unit ball of some dimension, such that the image is in fact a free boundary minimal surface, which is so, and such that this immersion is an isometry on the boundary up to rescaling of the metric. So that's the converse, if you want, right? So given a free boundary minimal surface, the coordinate functions are going to be Steklov eigenfunctions, but also the converse is true. Finding like a maximizer for the Steklov eigenvalue problem gives you a free boundary minimal surface. So there's like this correspondence here. And that's why what really revitalized the interest in these surfaces in the first place, in the recent years. Yeah. And now, a follow-up theorem, if you want, by Matheson and Pretridis states that such a smooth maximizing metric always exists, right? Given any surface, you can find a smooth metric maximizing this first Steklov eigenvalue. And this means that, in principle, any compact surface allows a free boundary minimal immersion into a unit ball of some dimension. Yeah. So let me stress, it's only going to be an immersion, and it might be a unit ball of higher dimension. Right? So this answers the question in a more relaxed setting. Yeah? You allow for immersions, you allow for codimension. So instead, what I would like to focus in this talk is the stronger question whether, given any surface, we can find an embedding into the unit ball of 3 dimensions, right? Because these are the surfaces we can actually see. Yeah. So this is the realization problem I would like to discuss, whether any surface can be realized as an embedded free boundary mineral surface in the 3-dimensional Euclidean unit ball. And of course, if such an embedding exists, is it unique up to isometry, yeah, up to ambient rotations? So these are the 2 main questions for the talk. And surprisingly, up until about 10 years ago, only 2 examples were known, like these 2. Yeah. So the flat disk has been known for a while, and also the critical catenoid has been known for many years. Yeah? I mean, it goes back to Euler, if you want. Yeah. But till about 10 years ago, no other examples were known. Right. So here the critical catenoid, you see, I mean, it's given by, you know, the usual catenoid with the right scale restricted to the unit ball, and then it will meet the ball exactly orthogonally. That's the free boundary situation. And so here we'll have a surface with genus 0 and 2 boundary components, while the disk is, of course, genus 0 with 1 boundary components. But are there any other examples? That's the question I would like to discuss right now. But of course, more examples have been found in the meantime. And the first non-trivial family of these 3 boundary mineral surfaces has been described in the paper by Fraser and Shane, and there's also a construction by Fola, Packard, and Solotareva. And this family of free boundary mineral surfaces has genus 0 and an arbitrary number of boundary components which are aligned along the equator. So these are pictures how they look like, right? So let me maybe mention this construction of Fola, Packard, and Solotareva only works if the number of boundary components is large enough. Because what they did is they took 2 flat disks, which are close together, including little half catenoids. And sort of, if you take many of these, you can have a configuration which is very close to 2 disks, and this can be can be somehow deformed a little bit to an exact solution. That's exactly what their construction is doing. But it only works for a large number of boundary components, right? That's not how you would get examples with 3, 4, or 5 boundary components. You would need a large number. Here I mentioned a conjecture in the recent work of Carlotto, myself, and Weigel about the Morse index of these surfaces. So I will not define the Morse index rigorously. Let me just tell you what it is in words, right? So let's recall these surfaces are critical points for the area, right? So this is like first derivative equal to 0. Huh? So let's make a second derivative test, right? Let's compute the second variation of area of this at these critical points. Okay, and then we get the stability operator, if you have seen it, right? We get some expression for the second variation of area. And we are asking what are these eigenvalues. So it's like asking what are the eigenvalues of the Hessian, right? Of a classic function. And so this so if you would see only positive eigenvalues, this would mean that any deformation of the surface would only increase the area. So this is the situation in the case where you have an actual minimizer of area. That's not the situation we are in here. Yeah. Free boundary minimal surfaces are always unstable in the sense that some of the eigenvalues of the second variation of area will be negative. Yeah. That's the reason for that is that the unit ball is convex. Yeah. So, for example, you can take the flat disk and translate it upwards, and to second order, this will decrease the area. And in fact, any example of these you can translate in at least one direction where you decrease the area to second order. Yeah? So this would correspond to a negative eigenvalue of the second variation of area. And the number of these negative eigenvalues is called the Morse index. Yeah? So here we conjectured that this Morse index in this case is equal to twice the number of boundary components. It's not known, it's just a conjecture. So this means that the more and more boundary components you get, the more and more unstable the surface become in some sense. Yes. So it's like computing the actual Morse index is an interesting open problem, and it's only known for the disk. There it's 1, simply the translation I mentioned. And for the critical calinoid, the Morse index is 4. That's known, but no other examples are actually known, right? So yes. Good question. You can again. So the disk you can only translate in one direction. The calinoid you can translate in three coordinate directions, and each of them would decrease the area to second order. But a calinoid you can also pinch the neck. That's the fourth direction. Yeah. And any other deformation will be sort of more oscillatory, right? And this will increase the area, like any orthogonal deformation to these, right? So that's why the Morse index is 4 in that situation. So no, you would, you would somehow, this is not exact, yeah, this is intuitive, right? So you would sort of, these translations are not the exact eigenvalues. You would want to restrict to the actual class, to stay in that class, right? This is sort of, where they come from intuitively, right? This is, I give them names, but this is not exact formulas, right? Yeah. Eventually, yeah, but it's infinitesimally anyway, right? So infinitesimal, you don't see the bending, right? So, yeah. So infinitesimally, you preserve the boundary condition by translation to the disk, right? So it's fine, yeah. Yes. Yes. No, we do not exceed. We do not. So this conjecture only refers to that family starting from 3. Starting with 6, yeah. Yes. To second order. To first order, it never decreases, right? To first order, it's always stationary. So to first order, any deformation will preserve or will sort of not increase the area. But to second order, right? It's like second. It's like sort of it's like it's like a parabola. Yeah. So let me tell you why Follapaka and Solitario are bothered gluing 2 disks to get these examples. They had another idea in mind. They wanted to punch a hole through the middle to get genus 1 examples, and they managed. That's how they look like. Yeah. So same construction. You take 2 flat disks, but you try to punch a hole. I'm not sure whether you can see it, right? You try to punch a hole through the center to get genus 1 examples, right? And now these surfaces have only been constructed for a large number of boundary components in a situation where you have a configuration very close to 2 disks. So these pictures are not in that situation. This is not, and are not in that regime. So 3, 4, and 5 boundary components are not considered to be large. Yeah? So these pictures are somehow conjectural simulations. And in fact, it's not clear how large the number of boundary components must be for the construction to work. Yeah? So we will see more examples like that in the talk. But genus 1 examples are known, at least for a large number of boundary components. Another cluing construction, which has been done, is taking our very first 2 examples, the flat disk and the critical calinoid, and intersecting. And now it's a good idea to desingularize that intersection by means of a Shirk minimal surface. Yeah? And this has been successfully done by Capoliers and Lee. And they obtained 3 boundary minimal surfaces with large genus and 3 boundary components. And there's an alternative construction by Ketover using equivariant min-max methods. But also in this construction, he needs the genus to be large in order to control the topology. So in either case, you would get examples with large genus and 3 boundary components. Again, we have a conjecture about the Morse index. So in this case, it's sort of 2 times G plus 6. Yeah. Yes. 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 That, yeah, most, yeah. Yes, exactly. Yeah, yeah. So here, here the conjecture comes is very simple, right? It's rather obvious why this should be. if you know the Morse index of the complete cousins of these surfaces, right? So people might have, you might have heard about the Costa-Hoffmann-Meek surfaces. They look similar, but as complete minimal surfaces in R3. Yeah? So these surfaces will not be restrictions of the Costa-Hoffmann-Meek surfaces. They will differ, most likely. Yeah? But still, the structure is close enough to use to make the following observation. Well, the index of the Costa-Hoffmann-Meek surfaces is 2 times G plus 3, right? So why would we expect the index to be 2 times G plus 6? Well, in R3, translations do not give index, right? Translations will not change the area at all, but translations in the unit ball will decrease the area to second order. That's why the index should be 3 larger than the ones of the Costa-Hoffmann-Meek surface, and the ones of the Costa-Hoffmann-Meek surfaces are now to be 2G plus 3. That's why conjecture is. Yes. It's known. Yes. Yes. But it's not obvious how you would transfer the proof. Huh? So R3 is a different situation. Yeah. I'm not sure whether you can localize the arguments to them. But at least that's the way the conjecture also. Another desingularization, this time by Caboleas and Weigel, respectively Caboleas and McGrath. Yeah? So here, on the left, 3 flat disks have been desingularized by Hartnegs in a very similar way as before, right? Before it was 2 disks, and you would get genus 0 with many boundary components. Here it's 3 disks, and you would get high genus, but 1 boundary component, if you look at it. Yeah? So it's a tripling. And over here, you have simply a doubling of the critical catenoid, desingularized by Nex. Yeah? And in each situation, you would get only examples for sufficiently high genus, but in this case with connected boundary, respectively with 4 boundary components. Yeah? So, right. So as usual, these kind of gluing methods need the genus to be very large to be in a situation where you are close to the models you try to glue. Again, the pictures are purely conjectural in a way that it's not clear whether genus 11 is large enough. Probably not for the construction to work, right? So that's but somehow the simulations still suggest they might exist. Yeah, but so far it's not known how to prove that actually exists for low genus in these situations. Yet another example. So very interesting work of Karpukin and Stern. They went back to the idea of maximizing the Steklov eigenvalue in the genus 0 case and showed that in the genus 0 case, you actually will be in the 3 ball, and the boundary components will somehow be distributed homogeneously across the sphere, right? So maximizing the first Steklov eigenvalue in the genus 0 case will lead to surfaces which have boundary components homogeneously distributed on the sphere in some configuration, and eventually you will converge to the if you let the boundary components, the number of boundary components go into infinity, will eventually converge to the sphere, right? It's a funny situation. Minimal surfaces converging to a sphere. Yeah? But of course, the boundary components somehow become dense, so it's not a contradiction. Yeah? And in an independent work by Caboleas and Xu, they also wanted to construct a family of rebounded minimal surfaces which converge to the sphere, but they had a different idea. They took many circles, and on each circles many boundary components, and they desingularized by minimal anoline between. Yeah? So that's how it looks like. And this configuration would also eventually converge to the sphere in a completely different fashion. Yeah, so they do not look alike, but they have the same asymptotic behavior if you want. Right. So a situation of genus 0 and large number of boundary components. Yeah? Yeah, so in this case, both of these surfaces have 60 boundary components, and they have genus 0. So prescribing the topology alone does not seem to be sufficient for uniqueness in general, at least for large topological complexity. Yeah, this is no surprise. Yeah. Yeah. In this case, so it was known that for large topology, for large topology would have different situations where you have. I mean, topology alone is not enough. Yeah. Yeah, that's a very interesting question. Yeah. But let me stress in this case, I mean, both have the same topology, but they have completely different symmetry properties. Right? This has very large symmetry group. Yeah. This one is not even clear whether it has symmetry at all. Yeah. So this is that's why how they, I mean, that's how they differ. But topology alone does not seem to be enough for the uniqueness. That's what we can infer from these constructions. Yeah. Yes. No, these are minimal. Mean curvature equal to 0. As to do for the catenoid. Yes. This is I mean, same here, right? I mean, these are not so different locally. If you just look at two necks separately, right? You would get a bending in this direction and another bending in this direction. Yeah, same situation. Yeah. Orthogonally. Oh, I wouldn't know that. I have no idea. Probably catenoidal. So it's maybe not far from, I mean, it's maybe not unreasonable to guess that very close to the, like these look similar to rescaled catenoids. It's maybe not unreasonable to believe, but I'm not aware of any proof. So these look like small catenoidal half-necks, you see, right? But that's what I would expect from, but it's not clear how to prove this. Yeah. So I would expect exact the same asymptotics as for the catenoid, but no. So let me summarize, right? All the examples we have seen either have genus 0 or high topological complexity, yeah, meaning large genus or many in the boundary components, right? So to really find existence proofs for examples with low genus and few number of boundary components turned out to be really hard, yeah. And for quite some time, it was controversial whether you can find an embedded free boundary minimal surface in the three-dimensional unit ball with genus 1 unconnected boundary, right? So this is here, like a donut with the disk removed. Can you embed it as a free boundary minimal surface in the unit ball? Yeah. And if you look at this genus 1 with connected boundary surface, like here on the left, it seems implausible, yeah, that you can somehow deform it to a free boundary minimal surface. But nonetheless, you can. Yeah. So this is our main existence result. In fact, there exists for any genus an embedded free boundary minimal surface in the three-dimensional unit ball, which has genus G and dihedral symmetry of order 2G plus 1. So this is a model of the genus 1 case. I also have a genus 2 somewhere. That's the one in the middle. So let me just give you. You can feel free to have a close look. This is, I will give it a. So this is a genus 2 case. This is a genus 1 case. As you can see, it works for every genus. This would be genus 3 here. I have a genus 4 situation. Who wants genus 4? Yeah, this is so it works for every genus. They have connected boundary. And so particularly interesting are the case with low genus here, of course. Yeah. So let me tell you, while you have a look at the model, let me tell you some more properties here. So I should tell you what the dihedral group is supposed to be. Because usually the dihedral group is the symmetry group of a regular n-sided polygon. Yeah? But here we are in the three-dimensional unit ball. So in this case, we somehow interpret the dihedral group as the subgroup of Euclidean isometries generated by the rotations of angle 180 degrees around this horizontal axis. Yeah? So you can try to find this horizontal axis in the model and rotate by angle pi, and you would see the surface is invariant. Yeah? That's the dihedral group. And by our very construction, it follows that this horizontal axis will be actually contained in the surface. Yeah? You can see it in the model if you look closely. And you can also say that uniformly for every genus, the area of the surfaces is strictly between pi and 3 pi. this will also follow from the construction. Okay, so let me tell you how we actually prove existence of these surfaces for every genus. So we use the equivariant min-max theory, which was developed by Ketover, based on the general min-max theory by Almgren and Pitts and Simon Smith and Colding Delalis, right? So I'm aware that some of you never used min-max theory before, right? So let me give you a very intuitive way of how to use it. Yeah. So, I mean, min-max theory is a big sort of chapter in the book of geometric measure theory, if you want. Like but you can use it as the theory as a black box if you want. And I tell you how. Yeah. So the first step in min-max theory is a very creative one, right? It's called a sweep out of the ambient space. And let me simply show you what we mean by sweep out. Yeah, without even defining a single word, we just run our sweep out, and you see it consists of model surfaces which literally sweep out the unit ball. Yeah? But they need to have some very refined properties, and I will tell you what they are. So first of all, it's like a family of surfaces, like indexed by a parameter t. And each of these surfaces has the right topology. In this case, they have genus 2 unconnected boundary. In general, you can have, I mean, here we sort of take like a middle disk and 2 small disks connected by little ribbons, and depending how many ribbons you take, you get each genus. Yeah? That's the idea here. And as you can see, it's we're managing to keep the area of each slice strictly below 3 pi. That's crucial in the construction. And while the small disks are away from the equator, it's not difficult to keep the area below 3 pi. It's simply enough to make the ribbons very small. But as you move closer, we are starting to get in trouble, because now the area of this slice is approximating 3 pi, and we want to stay strictly below. But there's a trick, it's called the catenoid estimate, which essentially says that one can stay below that threshold by somehow replacing these necks with unstable catenoids here. Yeah? And then it's a matter of simply retracting the surface, and we end up back with a horizontal disk. Yeah? So as you can see, the sweep out starts and ends from a flat horizontal disk with area pi, and in between it sweeps out the entire unit ball. I know what we do. I mean, none of these slices seem to look particularly minimal. Yeah. So none of them seem to look very good. But what's the idea? Okay, we want so think of the space of all surfaces as isotopic to the ones the space of all surfaces as isotopic to the ones we want to find as a space which somehow looks like that, right? I mean, we want to find an unstable critical point. It's a saddle point. Yeah. So this is the space of all surfaces. We want to find this saddle type critical point. That's an unstable critical point. How can we find it? Minimization is not an option. Minimization will lead to either 0 or at best, I don't know, the flat disk or something, right? But we have just defined a sweep out somehow from one flat disk to another flat disk, right? And in between, we have lots of surfaces which are all isotopic to the ones we want. Yeah. So this is our sweep out is somehow a path in this space of isotopic surfaces, right? So each point along this blue line is a surface, is a slice along the sweep out. So maybe this one corresponds to that point, and so on. And eventually we will reach, I mean, since we start and end from the flat disk, eventually we will somehow reach one of these slices will have maximal area. It's maybe this one, right? But unfortunately, it's not the critical point we look for. So what we do now is we add all other possible sweep outs which are isotopic to that one we constructed. Yeah? And for all of these sweep outs which are isotopic to the one we constructed, we isolate somehow the slice of maximal area. And among all these slices of maximal area, we try to find the minimal one. that's this min-max. That's why it's called min-max, yeah. Among all maximal area slices, we'd find the minimal one. And this is hopefully going to be the critical point you're looking for. Yeah? That's this mountain pass situation. So this picture is the reason why min-max works, right? And I mean, this picture is somehow like a two-dimensional situation, but the miracle is it actually does work in infinite dimensions as the space of surfaces, something like as the space of surfaces, right? That's the strength of this procedure, right? It's not only in this two-dimensional intuition where this two-dimensional mountain pass intuition where it makes sense, but it actually works in this infinite dimensional space of all surfaces. Yeah? Okay, so this is the picture. Let me also give you the formulas, right? So we look at the saturation. So we have a model sweep out called sigma t, and we add all other possible sweep outs which are isotopic, preserving the symmetry, right? So we have here an isotopy of the unit ball, which respects the symmetry group it's prescribed, and we deform the sweep out and we take all of these sweep outs, and then for each of such sweep out we take the maximal area slice and we minimize over all possible sweep outs. That's called the width, right? And now, if this width is strictly larger than the area of the first and the last slice, in our case pi, then the theory tells us there that there exists a so-called min-max sequence converging to a critical point, right? So the crucial part here is that this mountain pass condition is satisfied, that you actually have to go a little bit up before you go down. That the width is actually larger than what you're starting from. Yeah? In our case, we proved that using the isoperimetric inequality. In this case, it states that half balls have least perimeter, right? And in particular, if you're close to the perimeter of a half ball, which is pi, right? Then you're actually close to the half ball itself. So a surface which has area close to pi will divide the ball into something close to a half ball. That's the stability of the isoperimetric inequality. So suppose the width is equal to pi. Suppose you do not go above pi, then it will be always close to area pi along one sweep out. Yeah. So all the surfaces along the sweep out will be close to a half ball. But on the other hand, it's somehow the sweep out flips northern and southern hemisphere. Right, so you can't stay close to one and the same half ball all the time. That's a contradiction. That's how we use it. Yeah. So that's why we have to go a little bit up. That's the mountain pass. That's why it works. Right. Okay, so wow, we get simply by using the min-max theory as a black box without bothering about the hard work which went into the regularity theory. We got a min-max sequence which converts to an embedded, compact, connected, equivariant free-boundary mineral surface, gamma. Unfortunately, only in the sense of varifolds, right? So this does not control topology, right? So the main issue is that we have a sequence of smooth surfaces converging to something, to a solution, but only in a very weak sense. So the convergence does not preserve the topology, right? So even though our sequence of surfaces had the right properties, the topology might get lost or even gained in the limit. Right? So really the essence of the proof is to show that whatever limit we get from the min-max theory, it has the right topology in the end. Yeah? So the topological control is the essence here. Yeah? Right? Getting a solution is easy, but knowing how it looks like is hard. Yeah? Right? And the reason why we are able to control both the number of boundary components, which is 1, and the genus, which is arbitrarily given G, is that it's sort of exploiting these very concrete situations we're in. So we are exploiting the symmetry heavily. So essentially, the symmetry controls all the genus, and we're using the final properties of our sweep out in the end, right? So it's a very specific situation we are in, right? So we are using the very specific properties of our sweep out to control the topology in the end. But that's the key part of the proof. So I have some backup slides giving you all the details how we control the topology. So feel free to ask me in the end. For now, I'm going to skip this part and move on to the uniqueness question, unless you have urgent questions on this existence part. Yes. So you mean the discontinuity? So I mean, for the min-max theory, the mountain pass condition is enough. Usually this is what gives you this is the only condition you need in here. Yeah. I mean, there are different versions of min-max theory, right? We are using a version where we are working with smooth surfaces, right? This Simon-Smith. And in this case, if you have the mountain pass condition, the theory goes through. Yeah. You get the min-max sequence. But of course, that the limit is actually regular and everything. That's the main issue. That's the main contribution of the theory. Yeah. Okay. So to determine the genus and the boundary connectivity is the key here. I will not tell you right now, unless you can ask me later if you want. I have some slides explaining that. Let me move on to the uniqueness question in the interest of time. So we've seen many examples of free boundary mineral surfaces. Are they unique in some sense? Yeah. So let's start with the flat disk. Yeah. The flat disk is even unique in the class of immersed free boundary minimal disks in the n-dimensional unit ball. So the flat disk has a very strong uniqueness property. Yeah. So given any immersed free boundary minimal disk in the unit ball of any dimension, it's going to be the flat disk. So originally, this is work of Nietzsche for the three-dimensional case, and later it was generalized to any codimension biphase and chain. So here we have super strong uniqueness properties. Let's move to the next example. It's the critical catenoid. And the critical catenoid is conjectured to be unique in the class of embedded free boundary minimal annuli in B3. Right? And this is open. Uniqueness of the critical catenoid has only been shown under additional symmetry assumptions. So this is work of McGrath and Kuster-McGrath. For example, assume you have a free boundary minimal annulus, which has reflection symmetries. Then they can show it's the critical catenoid. Assume you have a free boundary minimal annulus, which is embedded and has antipodal symmetry. It's going to be the critical catenoid. But uniqueness is not known without symmetry assumptions. Very interesting recent work. It came out 31st of August this year by Fernandez, Hauswood, and Mira. They showed that embeddedness is really necessary for the catenoid. Right? The disk is unique in the immersed category. The catenoid is not unique in the immersed category. There are, in fact, immersed free boundary minimal annuli. They look like this. Yeah? In fact, infinitely many. Yeah? They have been constructed very recently. Yeah. So somehow any uniqueness proof has to use embeddedness. Yeah? So it's going to be hard, yeah? But very interesting open question. Let me also digress a bit and tell you that maybe you've heard of Lawson's minimal surface in the three-dimensional sphere, right? So Lawson has shown that any closed surface can be realized as an embedded minimal surface in the three-dimensional sphere. Yeah? And very recently, Capoleas and Weigel have shown, like some years ago, Capoleas and Weigel have shown that these Lawson surfaces, like some of the Lawson surfaces are in fact unique in the class of all surfaces with the same topology and symmetry, right? So Lawson surfaces have been known to be non-unique if you simply prescribe this topology. That's part of Lawson's work, right? So Lawson finds different examples with if the genus is not prime, for example. Yeah? But if you also prescribe the symmetry group, then the surfaces are unique up to ambient isometries. Yeah? So maybe the same is true in the free boundary case. Yeah? But as it turns out, in the free boundary situation, in general, even prescribing the topology and the symmetry group is not enough for uniqueness. Yeah? So in general, topology and symmetry of an embedded free boundary minimal surface do not determine the surface uniquely. And we found counterexamples. These two. Yeah? Together with Alessandro Carlotto and David Weigel, we have shown that for any sufficiently large genus, there exist two non-isometric embedded free boundary minimal surfaces in the 3-ball with 3 boundary components, genus G, and the same symmetry group, which in this case is the anti-prismatic group of order 4 G+1. Yeah? So again, I have some models of these, of course, right? So they come as a pair. So I give you them to you here. So you can compare these are surfaces both with the same genus, with the same number of boundary components and the same symmetry group. Yeah. Of course, we have seen this guy before here, right? This one is, we did not construct that one. We only had to construct the second, right? So the one on the left, you remember, the synchronization of catenoid and disk has been done by Capoleas and Lee. Yeah? So our contribution is to find yet another example with exactly the same properties, but different asymptotic behavior. Yeah? So this example here. Yes. Yes. No. No. It's almost. So the dihedral group is a subgroup of this. The antiprismatic group is the dihedral group, which I explained, plus reflection symmetries are across word. It's no. So if I don't know where the model is, but the big one. Do you have the big one somewhere? Ah, yes. I want them back, by the way. Yeah. So look, the antiprismatic, actually, it turns out that this is going to have also the antiprismatic symmetry group. Yeah. But we do not prescribe it in the construction. Let me explain. So the dihedral group is only generated by these movements here. That generates the dihedral group. What I'm ignoring here is that apparently you also have reflection symmetries across vertical planes. Yeah, which these reflection symmetries do only turn up in the simulation. We do not prescribe them. They seem to appear a posteriori. Which is open, by the way. We did not show that. But somehow it seems to have more symmetry than we prescribe. But interestingly, it's enough to prescribe only the dihedral group. And there's an advantage to not prescribe reflection symmetries for the regularity business, right? So prescribing only rotational symmetries is better for regularity because it's sort of, less singular. The singular locus is smaller, right? Just the line is better than the plane of. Yeah. So for regularity issues, it's better to prescribe only rotation symmetries. But the symmetry group is going to be the same conjecturally. Yeah. Yes. So let me tell you a little bit more about these surfaces. Right. So both families, in fact, are constructed using gluing methods. So I told you this one is the disingulation of catenoid and disk. And this one is also some sort of a gluing construction. I will tell you how exactly we do that. So they have the same topology and symmetry, but they have still different properties, of course, right? So this one has equivariant index 1, while this one has equivariant index at least 2. So remember what the index was. This was the number of negative eigenvalues of the second variation of area. So now restrict to deformations which preserve the symmetry. That's the equivariant index. Yeah. So there's one negative direction for the second variation of area which preserves the symmetry, and here there are at least 2. Simply, these necks can be pinched. Yeah. And here this situation doesn't happen. That's why this has more equivariant index. That's the idea. And an interesting open question is what is the lowest genus for which these surfaces exist? Yeah. So here the picture suggests genus 11 works. Yeah. In our proof, we need high genus, right? By high genus, I mean something with many zeros. Yeah. It's not known how large the genus has to be, but like 10 to the to the something, really high. Yeah. So 11 is not high. But it's an interesting open question how large it has to be actually in reality. Yeah? The proof needs high genus, but how is it in reality? And somehow, probably, conjecturally, both families of surfaces exist all the way down to genus 2. Yeah, I have some small models showing that. You know, that's another pair. So, want to have a look here. I take that back. I'm taking offers, you know. How yeah. Okay, yeah, conjecturally they exist also for small genus, but the proof doesn't give any hint whether this is true or not. Yeah. Also, curiously, we have no evidence for genus 1. Yeah? Yes. It's an implicit function theorem argument. You don't get any information. I will show you. I will show you exactly. So that's the proof, by the way. So I will show you the proof in pictures, and it will be clear from why there can't be any control, I think. So these are the ingredients we want to clue, obviously, right? So it's the flat disk in the middle. It's sort of catenoidal, minimal annuli on top and the bottom. So let me stress here that we allow a small gap on the equator. It's the parameter b, which we allow to vary, right? And what we want to clue in is a generalized Scherk surface. It's a Karcher-Scherk tower. And they exist as sort of, you know, 3 disks intersecting if the angle is very symmetric. But they also exist for any other angle. In this case, they are sort of 6 planes not meeting exactly in the vertical axis. So they will have some offset here in red. But they exist in actually for any prescribed angle here, these Karcher-Scherk surfaces. So you can take 6 planes somehow, and you get sort of a Karcher-Scherk surface with. So if you have any angle, you get some offset here, which gives you this Karcher-Scherk surface with that asymptotics. Yeah. So this has been known to exist. Yeah, and that's the model which we somehow want to clue in along the equator. So we can sort of gauge this angle here to exactly that angle here. Yeah? So we can take exactly, so we can compute which angle we will have along the equator, and we use the same angle in the Karcher-Scherk surface. Now we could also compute what the distance is here and use the exact same distance here. So we could optimize both parameters, but we do not, and there's a reason. So we leave one parameter free. It's important. I will tell you why. And we leave this gap we leave as a free parameter. Okay, so first thing you do is we need to wrap around this Karcher-Scherk tower along the equator, and we do that very brutally, right? We simply, you know, take g+1 periods of that tower, rescale it such that it has height 2 pi, and we simply wrap it around the equator somehow. Yeah? I mean, this is explicit coordinates called equatorial coordinates. You know, you simply wrap it around. Yeah. It will destroy the minimality, but we have to correct for that anyway. And then the idea is to interpolate with these catenoidal pieces. Yeah? Right. So this is how it looks like. Here we have this rescaled Karcher-Scherk towers very close to the equator. And unfortunately, sort of the way our coordinates we use somehow makes them bend downwards in an awkward way. And we somehow need to interpolate with something going upwards, and it looks very ugly here. And it's going to be very non-minimal. But the idea is that sort of increasing genus, the genus, like increasing the genus G here, right, makes everything move to the equator. And close to the equator, the coordinates are very fine, and the disturbance, like the error is very small, right? So increasing G makes everything better and better and better and closer to minimality. Yeah? So even though the interpolation looks horrible at that stage, the closer you move to the equator with the gluing, the better everything gets. And then, of course, the idea is to perturb this initial surface again to exact minimality while preserving everything else. Yeah? It's already orthogonal along the boundary, right? Both the Scherk piece and the catenoidal piece are already orthogonal on the boundary. But then you want to sort of perturb this gluing bit a little bit to exact minimality. And this is, of course, an inverse function theorem kind of argument. The configuration is already very close to minimal. So when do we know that there's an actual solution close by, right? It's like an inverse function theorem argument. You have an almost solution. If the gradient is non-zero, there's a solution close by. So we need to compute somehow the gradient here. So we linearize the problem. This is again somehow the same operator as for the second variation of area, if you want. Unfortunately, it's not quite invertible in this situation. It is. It doesn't have kernel, but it does have co-kernel. I can tell you what I mean by that. So we need to linearize this. I mean, we can write down exactly what we want to solve, right? We're looking for a small perturbation which gives you exact minimality. It's a nonlinear equation. We compute a linearization. And it's a linear equation. I call it JU equals F. Yeah? That's how it looks like. But we're trying to solve that on each piece individually as a first step. Yeah? On the cardinoidal piece, on the disk, on the Shirk piece. Yeah? On the cardinoidal piece and the disk, it's not a problem. But the Shirk piece has these asymptotic planes, right? It's non-compact in some sense. Yeah? As a model piece, yeah, somehow has these asymptotic planes. So we have to use function spaces which somehow impose a decay, like an exponential decay along these wings of the Shirk surface. And now, even if you prescribe data F, which has the decay along the wings, the solution does not necessarily share that decay. Right? Think of the equation Laplace U equal F, and F has exponential decay. Then U does not have exponential decay necessarily. Yeah? Right? Yeah. Harmonic functions do not have to be zero. Yeah. So, that's what I mean by co-kernel here. So the solutions U, even though the data goes to zero, the solution U could approach a constant instead. And the way we get rid of this issue is by something called Lyapunov-Schmidt reduction. And so intuitively, U is the deformation which makes the surface closer to an exact solution. And somehow, maybe along the Shirk wings, the solution approaches the constant. The required deformation does not go to zero along the wings of the Shirk surface. So intuitively, we can match that with this parameter B with the gap between the cardinoidal piece and the equator. Yeah? So intuitively, we can vary B such that it exactly fits that non-zero constant. Yeah? So that's why I had to vary the parameter B in the end, and that's how we can get rid of this co-kernel in the end, by letting this one additional parameter also to vary. And then we can sort of iterate this procedure to get an exact solution. But again, we need the genus to be sufficiently large in an implicit way for it to work, and that's why we do not have any lower bound. Yeah. Yes. Yes. You would get something in the order. I mean, you can start even earlier, right? So I mean, I actually did that. So in this picture, yeah, we can compute what error we have here actually, right? And for this error to even make sense compared to the rest, this error has to be small in some we can compute somehow the order of magnitude of that error we get here. And for this interpolation error to be in a reasonable order of magnitude where all the other quantities even make sense, the genus has to be larger than 1000 already. Yeah? So, but simulating for genus 1000, you can't see anything anymore. Yeah? So the genus will be like, the construction will, the way we could set it up already requires the genus to be so large that you don't see any difference anymore, right? So that's the only answer I can give you. Yeah. Yeah, so in my opinion, this lower bound is somehow meaningless because it doesn't give you, it doesn't say this picture exists, you know, because you can't in this regime you can't see anything anymore anyway. Yeah? But exactly, it's already so large that the picture you cannot see it with your eyes anymore. Yeah? But you know that some large genus exists, after which exists for all others, for all higher ones. Yeah? So it's only an existence theorem, in some asymptotic sense. Yeah? But any lower bound you would extract from the construction is meaningless, in my opinion, because the construction is, for it to work, it's very suboptimal already. Yeah? I mean, it's not sharp at any stage of the gluing. Yeah? Yes. So really, the interesting part is that you can't find two examples with the same topological properties and the same symmetry. Right? And even if it's only asymptotically, that's the key here. Right. So to get the low genus examples, other methods have to be found, right? And min-max would be a good candidate, right? I told you about min-max. So let's try to find these surfaces with min-max. But how can min-max distinguish between these two? Yeah, not at all, right? So even if you try to set up a min-max construction, it's completely unclear which of these two surfaces you would get, yeah, in the low genus regime. Yeah, so it's not so clear. Maybe one of them, but not both. Yeah, they are homotopic. They can't be distinguished by min-max. Yeah? Okay. So I think that's all I wanted to show you about this gluing construction. It's very technical, but the idea is rather straightforward in that sense. It's like an inverse function theorem kind of argument. And all the other gluing constructions somehow work similar, but specialized to each individual case. Yeah. That's the message I wanted to tell you. So let me summarize what I've told you. Remember the existence question, right? So our main contribution was to show that surfaces with arbitrary genus and one bounded component exist. That's this row here. Other peoples have shown that genus 0 and any number of bounded components is possible, or genus 1 and large number of bounded components, or if you remember, you know, the surfaces by Kappelus and Lee, and our second family, 3 bounded components and large genus is possible. And if you remember the doubling of the cardinoid, 4 bounded components of large genus is possible. But all the other situations are still open. Yeah? So the existence, the realization problem is wide open if you look at this table. Yeah? So especially for, you know, this low topological complexity regime, very difficult problem to actually construct them. Yeah. So by now, numerically, I can give you simulations for almost all of these question marks, but to develop methods to prove the existence is a completely different question. And this is wide open. Say again? You mean this diagonal? Good question. Probably I could cook something up. No, conjecturally, yeah, but they most likely should. They exist most likely. Yeah. Yes. Right. It would be interesting to see the diagonal. Yeah. Yes, that would be actually very interesting. Yeah. So here's one construction I would cook up. Yeah. I haven't tried that yet. It's purely my intuition. Let's go back to this. Who asked the couple years, Lee? Yes, perfect. Yeah, we'll take this one. So take this one, yeah. This one has a high genus already. Now maybe it's a guess I haven't tried yet, but let's think of, you know, put another flat disk here, yeah, and desingularize with many little bounded components. You know, this would give many bounded components and high genus, yeah. Or you can put also one below, yeah. You can sort of put a like a pot, like a lid on a pot, yeah. Yeah, I mean, I don't want to do the proof of that. Yeah, I mean, the proof would be a nightmare to control both situations simultaneously somehow. But intuitively, you could sort of add like a flat disk here and desingularize with many necks here by some sort of a Zerg type. So this would give an example with large genus and many number of bound components. But many other constructions could be possible. Yeah, that's only one way of thinking of it. With a little creativity, you can cook up situations that should work. Yeah. So another situation which definitely works is a stacking. So I showed you 3 disks work, 3 flat disks. So take multiple flat disks and is singularized by many necks, and you can have sort of lots of vertical boundary components this way, and high genus. This definitely also works. It looks like a hamburger, this surface then, right? And so this will have large genus and many boundary components, and this most certainly works. The stacking procedure. There's a sketch in Capoleas's work how he explains it, how he would set up a proof of that. The details are not formulated, but all the ingredients are there. The stacking method most certainly works. Yeah, thanks for the question. Okay, let me maybe move on with the discussion here. So to summarize the uniqueness, wide open. Yeah, we have shown that like in chat there exist 2 pairwise non-isometric pre-boundary minimal surfaces with the same topology and symmetry, but still there's hope to get uniqueness for low topological complexity. For the catenoid, it's open. Yeah, maybe this one is unique. Yeah, maybe. It's completely unclear. Yeah. So and just as a final remark, I want to draw your attention to something which relates a little bit to the previous talk by David. I would like to ask, specifically in the genus 0 case, how are the boundary components distributed? Yeah, in the genus 0 case. And there has been an interesting observation by many people, including myself independently, that somehow if you take the pre-boundary minimal surface of genus 0, it somehow corresponds to the Steklov maximizer, then the boundary components are arranged in a similar way as electrons would arrange themselves on a metal ball to minimize the Coulomb potential, the Coulomb energy. And that's an observation which is very sort of tempting to make, that there must be some relation. But the question is, what is the relation? Yeah? So why do boundary components in the genus 0 case want to interact like electrons in a sphere, in a qualitatively similar way? And to find out the boundary configuration in genus 0 case would be super interesting. Let me give you one reason why it would be super interesting. If you look at the numerical simulation for 61 electrons in the sphere, you will find the minimal energy configuration does not have any symmetry. So that's why I would conjecture that there exists a free boundary minimal surface, genus 0, with 61 boundary components in the Euclidean 3-dimensional unit ball, which does not have any symmetry, like trivial symmetry group. Yeah, because it corresponds to that Thomson configuration. Yeah? But only for 61 boundary components. And the next case without symmetry would be 140. Yeah? And all the other cases in between would have some symmetry or another. Yeah? And with this conjecture, I would like to end the talk. Thank you very much.
Thank you, Mario, for this amazing talk. Are there question, remarks about this? Okay, if there, Alessandra's got one.
You want to see the control topology? What do you want to see? The genus or the boundary? The genus. Yes, let me show you controlling the genus. Yeah. So remember, so we found a limit of our min-max sequence, which is a free boundary minimal surface, of something, so we know the limit realizes the width as its area, which is strictly larger than pi. That's the estimate we had. Yeah. Okay, so it's not, at least not isometric to the flat disk. And according to Nietzsche's uniqueness result, it can't be a topological disk for that reason. Yeah? So we know it's not, whatever our limit is, it can't be a disk because of Nietzsche's uniqueness result. Yeah. Otherwise, you would have area pi, and the width is larger than pi. Okay. Now we need to show that the boundary is connected first. That's the first step. But once we know it's not a disk, but it has connected boundary, it has genus at least one. Yes. And then there's a general statement in min-max theory that while the genus can decrease, it cannot increase. Yeah. So let me elaborate on that. It's reasonable that min-max sequence destroys genus, because remember our sweep out. Maybe we could have, just for fun, added very small handles to our sweep out just for decoration. Yeah, decorative handles in our sweep out would have disappeared in the limit. Yeah, and that's a good thing, right? Because so if we had done that, they shouldn't be there in the limit. So imagine, and our sweep out would have had sort of very small decorative handles along the sweep out. They should be gone in the limit. Yeah, so genus should decrease in limit, but it cannot increase. That's part of the min-max theory. So we know our surface has genus between 1 and g, and then we prove a general structure of equivariant surface lemma, stating that any connected properly embedded equivariant surface with genus between 1 and g must have full genus g. Right? So that it seems a very strong lemma, but the point is that the symmetry we impose corresponds exactly to the upper bound of the genus here. Yeah? So surface with equivariant, which is equivariant with respect to the dihedral group of order 2g plus 1, and genus less or equal than g must have full genus g. Yes. Yes, it's the symmetry controls the genus. Yes, exactly. That's the trick here. Yeah. So to control the boundary, we use the structure of the sweep out instead. Yeah. Yes. Yeah. Thanks for this question. Yeah.
Okay, if there are no other remarks, I'd just like to ask a question that I think may be of interest for many people. Can you tell us something about how do you construct these beautiful things? Or
so these are 3D printed. Yeah. So I use. The pictures are made by simulations. Yeah. So so I use a very old program. Maybe you've heard of Ken Bracke. Yeah, so he's one of the inventor of mean curvature flow. Yeah, and he's also the inventor of a program called Bracke's Surface Evolver, and it's a program from the 90s, and it still works very well. And with that, you can. Yeah. So the problem here is, what this program does is essentially it implements the gradient flow of area. Okay. So it's very easy to find somehow absolute minimizers with that. It's a bit delicate to find these saddle points. Exactly. So it's a bit, it needs to be a little bit, it needs it does not always work. Yeah. Yes, exactly. So with a little bit of, tuning on the initial configuration, you can still get all the way to critical points. Yeah.
So you start from something similar to what you're expecting.
Exactly.
This is the point.
Yeah, yeah.
But okay. But is it something that's mathematically true that these things, if you start from something similar to what you constructed and you evolve it through Bracke flow, mean curvature flow, you reach for
not known.
It's not known.
No.
It's very interesting.
Imagine you would have to solve a gluing problem for that something, right? Imagine you have a surface close to an actual solution.
Yeah.
Or like close in the mean curvature sense. Imagine you have a surface with mean curvature almost to 0 and orthogonal almost orthogonal, with the boundary almost orthogonal. Perturb it to an actual solution. That's a gluing problem with one piece. Yeah. However, the gluing only works with very simple ingredients. Yeah. The gluing only works with ingredients which you understand completely. Yeah. Disk, you understand completely. You know all the eigenvalues in the disk of the Laplacian, say. You understand the cardanoidal piece completely. Even the shirk piece can be understood completely. But if you have a general almost solution, it's unlikely that you understand it well enough to do the gluing argument, like the perturbation argument.
Okay, and if you start closer in a stronger topology than the one you
would still, I
mentioned?
mean, what you would have to do is to invert the linearized operator, right? So you write down the linearization of your, I mean, it's the Jacobi operator, yeah. Yes, I mean, yeah, it's you need to understand the Jacobi operator of whatever surface you have completely to say whether it's invertible or not. Yeah. And there's hope to do that if you understand the pieces well, right? The Jacobi operator for the disk is just the Laplacian, right? So you can understand that. But if you do not know what a second fundamental form is, you cannot understand the Jacobi operator well enough to say whether it could be invertible or not. Yeah. It's minus the Laplacian minus second fundamental form squared. Yeah. Yeah. No. The second fundamental form is tends to be very large, close to the genus, like to the whenever there's genus around, like yeah. I mean, it's not a perturbation from the Laplacian. Yeah. Second fundamental form is not close to 0. Yeah. Mean curvature is close to 0, but not a second fundamental form. Yeah. Yes. Yes. So maybe you could do it in some situations, but it's not obvious how to make this rigorous. Yeah. It's a good point, yeah, but it's only numerical information, yeah. Maybe it's actually a good suggestion. Maybe with more numerical information, one could try to make some argument, and this is in fact a work in progress, actually. Yes. 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 So if you allow if you allow the input of more numerical information, there's hope to say something to make it somehow rigorously validated. Yeah, but this is work in progress. I can't say anything at the moment about that. Yeah. But thanks for the question. It's a very good suggestion. This would give at least some avenue of arguing for the existence of all the simulated examples. Yeah. Yes. Exactly.
And a mathematically deep question, and then you print the picture you find when
Yes.
numerically directly through the 3D printer.
Exactly.
Ah, see. Okay.
Yeah.
Thank you.
It's a lot of fun. I mean, you would be surprised. Like many sort of departments actually already have a 3D printer if you ask around. Yeah. So it can be a fun interdisciplinary project with whoever has one in your department. Yeah.
Okay, so if there are no other things to ask or comment on this talk, we thank Mario again.
Thanks a lot.
And we conclude here the workshop. I hope you enjoyed it. I warmly thank all the speakers for having delivered such beautiful talks exactly in the spirit me and Alexandra hoped for. We thank all the participants, and we want to thank the staff of the Centro de Giorgi, who make organizing events like this extremely easy and very funny. Actually, it's not stressful at all. Really, it's something amazing. Professor Marchiodi for always being so supportive towards sort of any initiative. So in particular, this is one, and also the staff of Scuola Normale who helped with the technique, with the computer and so on. And thank you all again for having been here.